Let's go through this standard and talk about the growth and decay. First of all, for growth, the graph starts very slow and then goes really fast in the upward direction. Whereas with decay, it instead will start from a very fast upward direction, but then slow down and get very close to the asymptote, but not cross the asymptote. How do we know whether it's growth or decay? Depends on the actual formula. So when you look at the formula, which is y equals a times b to the x, what you have to look for is that the exponent x is the variable, but it's a and b that you're going to use to determine whether it's growth or decay. A is the initial value, but when b is greater than 1, then it's a growth problem. But then when b is between 1 and 0, it's a decay problem. So you can look at the equation itself and determine whether it's going to be growth or decay by looking at the value that has the exponent with the variable on it. So in this case it's b, and if it's greater than 1 it's growth, if it's less than 1 it's decay. Now just below this we have a couple examples of this. So if you look at the first graph that we're going to do here, that one's going to be growth because the 3 to the x power is larger than 1. And then the next one, because the thing that's to the exponent of the 1/4, that's going to be decay. So let's do the first graph. Okay, this is going to be a little sloppy because of the fact that I've got to do it with my finger on the graph. So bear with me as we do it. Let's set up our axes first. What we're going to do then is we're going to come up with, using on our graphing calculator, look up the table. It's important that you find the table to get values. So if I put in values starting with, let's say, starting with -2, I get right off our table on the graphing calculator 0.2. Sorry, that keeps coming over because I'm on the edge of the document. If I put in -1 into the original equation, you get 0.7. If you put in 0, you get that initial value of 2. Notice that's the thing in front of the 3 to the x. And then if you put in 1, you get out 6. And if you put on 2, 2 times 3 to the second power, that's 2 times 9 is 18. Now, let's plot these points. On the y-axis is when we have that 0, 2. And then if we plot 1, 6, and then the graph goes up really fast after that, so just make sure we go through those points, and then it's really close to the axis to the left of the y-axis. That's called an asymptote because we don't cross it, we just get very close to it. Let's do the same thing for the next graph. Sorry, this can get my picture is actually covering over some of what we're working with. So let's set up our XY table first. In putting the x and y's in, notice that since the exponent on this one is an x minus 3, we're going to start a little bit larger. So if we put in 1, we get out 16. Put in 2, you get out 4. Put in 3, you get out that 1. Put in 4, you get out 1/4. And if you put in 5, you get out 2/16. Now this time, the numbers to the left of the graph are very large, so we'll plot those points first. So it's going to start out very large, and then it's going to get really small really fast. That's called exponential decay because it starts out large and then it gets really small, and those really small values are still really close to the axis, which is the asymptote. So draw the graph and through the points, using the table that we got from our graphing calculator. All right, so the asymptote again is the x-axis. All right, let's try a word problem. This one's going to be a depreciation problem. Okay, so when we put these values in, what you're going to get is using our depreciation equation of a of t equals a times 1 minus r to the t power. Okay, if you put in a, that a value is going to be 35,000, which is going to be covered over here a little bit. So I'll read to you what we're getting, 35,000, and then it's times 1 minus, since it's 6%, 1 minus 0.06, all to the t power. Well, 1 minus 0.06 is 0.94. So our equation becomes 35,000 times 0.94 to the t power. All right, now let's actually put in some of these values. It says after 3 years and after 10 years. So we're going to start off by putting in the 3 years into it. So a of 3 is going to equal that initial value, 35,000. Then we're going to have our 1 minus 0.06 was 0.94. So 0.94, and in this case we'll put it to the third power. If you do that on your calculator, you get a total of, in this case, $29,070.44. Now if we do the same thing for putting in 10, so we take a of 10 and put 10 into the spot, which is the exponent, that's going to equal, when we do it, again, it's if we took the 35,000 times 0.94 to the 10th power, you get $18,851.52. So $18,851.52. That's how much the car is worth after 10 years. All right, let's solve for x in these next couple problems. The steps for this, remember, are to get the same base on both sides. So we get 4 to the x equals 4 to the third, because 64 is 4 to the third, so x equals 3. The next one is we get 3 to the x plus 4 power, and that equals 27 to the x. Well, 27 is 3 to the third, so you get 3 to the x plus 4 power equals 3 to the 3x. That means x is going to equal 2. I'll scroll up here so you can see that a little bit, see the work on that one. If you need to, you can pause the video to kind of catch up to what it says here. There you go. All right, the next one is 5 to the x equals 25 to the x minus 2 power. So we'll make that 25 into a 5 squared to the x minus 2 power. So now we multiply through on the right side, make that 2 times x minus 2 is 2x minus 4. And so we can set the exponents equal since the bases are both 5. So you get x equals 2x minus 4. And then solve that equation, and you get x equal to 4. Let's do the same thing with the last one. So this one's going to be covered over just a little bit in some of the work. So let's get it set up first. 6 to the x plus 2 equals 216 is 6 to the third to the x power. So on the left side we get 6 to the x plus 2, but on the right we get 6 to the 3x. So we can, since we have the base of 6 on both sides, we can set the exponents equal. X plus 2 equals 3x. We solve that equation and we get x equal to 1.